Hi, this is Sriyank Siddhartha and welcome to the next video on this Kotlin coroutine series. In this one single video, you will explore everything you need to know about Kotlin CoroutineScope, CoroutineContext and Dispatchers. Now the topic of CoroutineContext and Dispatchers is something which is like a nightmare for every developer. So I will try to answer all your small and big questions. So stay tuned with me until the end of this video. So yes, let's start with Kotlin CoroutineScope. What it means actually. Well, we all know that launch function is a coroutine builder. It creates a coroutine. Now, when it creates a coroutine, then by default it gets attached to a special instance of CoroutineScope. So, within this lambda expression, if you use this keyword, then basically you will get access to the CoroutineScope instance. So in short, every coroutine has its own CoroutineScope instance attached to it. And this is something you need to remember. Similarly, the coroutine builders like async or runBlocking coroutine builders also has a CoroutineScope object attached to it. Fine, I hope you get it. So here we have runBlocking coroutine as a parent coroutine builder for this main function, right? So when it creates a coroutine, then attached to it we have the instance of CoroutineScope, which you can find it here as a hint by the IntelliJ IDE. So within this lambda, if you use this keyword, then you will be able to access the CoroutineScope object. So if you print this keyword using a print statement, then let's see what happens. Let us run the program. So here this entire output represents a CoroutineScope object. Also the signature of CoroutineScope shows what kind of coroutine was created. Since we were using a runBlocking coroutine, so that's why it is showing a blocking coroutine that blocks the main thread, right? And this active shows that when this statement was executed within the coroutine, then the coroutine was in active state. And right after this we have @some value, right? So this value is basically the hex value. And this hex value represents the hash code of the object. So basically this hash code represents the uniqueness of the object. Fine. Now similarly, if you use a coroutine such as launch coroutine or async coroutine builders and print the CoroutineScope objects using the print statement like this and run the program, then you will find that the launch coroutine builder creates a standalone coroutine and the async coroutine builder creates a deferred coroutine which returns a deferred job object. So basically the CoroutineScope represents what kind of coroutine you have created. Quite simple, isn't it? Now what about the CoroutineScope of the child coroutine? So here within this launch coroutine, if you add a child coroutine like this and call it child launch, run the program and let's see what happens. Then you will find that this is the parent scope of launch coroutine, right? And this is the CoroutineScope of the child coroutine. So here you will notice this CoroutineScope and this CoroutineScope instance are different objects, which you can make out using the hash code value, right? They both are different. So this shows that every coroutine, irrespective of being a parent or a child, has its own CoroutineScope. Nice and simple. Now moving on, we have CoroutineContext. Well, this topic is going to be a bit tricky, but don't worry, we will tackle it in our own way. Well, similar to CoroutineScope, every coroutine has its own CoroutineContext, but with a twist. As mentioned, the CoroutineScope is unique for each coroutine, right? But CoroutineContext can be inherited from parent to child, meaning the child coroutine can inherit properties from the parent coroutine. Now this coroutine context has basically two major components, such as a dispatcher and a job object. Now this dispatcher is very important. It is the dispatcher which decides on which thread the coroutine will execute. So please note this, it is the dispatcher which decides the thread of the coroutine. This is very important. And you are already familiar with what this job object means and how using the job object you can control your coroutine. I hope you remember this from the previous videos. And apart from these two, you can also assign a name to the coroutine. Fine, which we will explore later. So let's understand things better in a demo. Now here we already have some code which you can get from the link in the description. So for the next few minutes I would suggest you to just focus on what I am saying. Don't worry about the code. You can anyways get the code from the GitHub link in the description. Well, just now we talked about the CoroutineScope, right? How with every coroutine there exists a CoroutineScope. So similar to CoroutineScope, with every coroutine there exists a CoroutineContext. And within this coroutine of runBlocking, if you want to access the CoroutineScope, then you can use this keyword, right? Which we saw just now in our previous demo. Similarly, if you want to access the CoroutineContext of this coroutine of runBlocking, then in that case there exists a property of CoroutineContext. Fine, so using this property you can always access the coroutine context of the current coroutine. Great, so let's document it. Now let us see how the coroutine context play a role in determining the thread for each coroutine. Let us start with the coroutine without parameter. Well, this is also known as confined coroutine, which I will talk about shortly. So when you create a coroutine without any parameter, like this, then it is going to inherit the coroutine context from the immediate parent. That is, this coroutine is going to inherit the coroutine context of the parent runBlocking coroutine, which means this child coroutine of launch is going to execute on the main thread, which is the thread inherited from this runBlocking coroutine, right? So here, let us use thread main as a comment, so as to avoid any confusion. So if you type a print statement over here, then this statement should execute on the main thread, right? Let us run the program and let's see the proof. So here we go, the coroutine C1 was executed in the main thread. So here is the proof, right? So in short, just remember, when you create a coroutine without passing any parameter over here, then it will inherit the coroutine context, that is, it will inherit the dispatcher from the immediate parent coroutine. Great, isn't it? Now next, we have coroutine with parameter, and this time we are going to pass such as Dispatchers.Default. So if you use Dispatchers.Default like this, then this will create a coroutine whose properties will be exactly same as the coroutine created by globalScope.launch function. That is, this will create a coroutine at the application level, and hence it will execute on a separate background thread. And I hope you remember the properties of globalScope.launch function, which we explored in the very beginning of this Kotlin coroutine series. So again, let us print and check the name of the thread. Name it C2, run the program. So here we go, the C2 was executed on a separate background thread. Fine, so here is the proof. So let us assume this thread name is T1 for the simplicity. Now here let us add two more lines of code, such as a delay function of 1000, and then let us print the thread name again, right? Now, in case of global-scope.launch coroutine, if you remember in the very first video of this series, we explored that suppose this statement gets executed in thread T1. And after this, suppose we execute a suspending function such as a delay function. Then in that case, the thread T1 gets released. And after delay function gets executed, when the next statement is executed, then it will either execute on thread T1 or even it can execute on some other thread, right? So here we can mention thread T1 or some other thread, depending on the thread availability. And here I think let's use C2 after delay, so as to avoid any confusion. Run the program. So here we go, C2 was executed in default dispatcher worker 1. And after delay, it is a coincidence that it is getting executed in the same thread, right? So just make a note, this thread can change after the suspending function gets executed, just like in case of global-scope.launch function. So in short, this Dispatchers.Default is exactly same as that of the functionality of global-scope.launch function, right? So please don't get confused here. Now moving on, we have Dispatchers.Unconfined parameter. So let's create a coroutine and add a print statement. Let's name it C3. Great. Now when you use the Dispatchers.Unconfined dispatcher, then in that case, this coroutine is going to inherit the CoroutineContext from the immediate parent of runBlocking, right? So that's why this statement is going to execute on the main thread. So this is the property which you need to remember in case of this dispatcher. But right after the delay function, which is a suspending function, and suppose we add a print statement over here, such as C3 after delay, then this statement is going to execute on some other thread that is not the main thread. So here instead of T1, we can use some other thread, which will be assigned from the shared pool of thread, right? So let us run the program and let's see what happens. So here we go, this is the C3 initially got executed in the main thread, and right after delay function, it was executed in some other background thread, right, whose name is this. Now in the end, in the first case, we actually did not notice what will happen if you add a delay function over here along with a print statement. Well, let me tell you what will happen. Well, in case of a coroutine without any parameter, the execution of the suspending function does not affect the thread of the subsequent code. That is, this statement will continue to execute in the same main thread, which was present in this first statement, right? So please note this. Now I am sure at this point of time you might have got jumbled. So let us quickly summarize what we have explored so far. So in the first case, let us expand our comment. So in the first case, where we are creating a coroutine without any parameter, this will inherit the coroutine context from the immediate parent, right? Hence, the dispatcher provides the same thread as that of the parent. Fine. And even after the execution of the suspending function, the coroutine continues to execute in the same thread. So in short, the coroutine remain confined to the same thread. And as we all know that the thread which is being assigned to a coroutine is decided by a dispatcher. So that's why the dispatcher of such coroutine is known as confined dispatcher. Just because we are confined to just one thread. Fine. So next, we have a coroutine with a parameter of Dispatchers.Default. Well, Such coroutine is exactly same as globalScope.launch builder. So they get their own coroutine context at the application level. So the dispatcher here provides a separate background thread. Let us assume it is T1. But after the execution of the suspending function, it might change its thread. So please note this. It will then get executed either on thread T1 or in some other thread. Fine. Next, moving on to our third case, which is Dispatchers.Unconfined. Well, this dispatcher is also known as unconfined dispatcher. Why? Well, in this case, the context is inherited from the immediate parent. But after the execution of the suspending function, the coroutine executes in some other thread, right? Which you can see using this print statement. So in short, the coroutine is not confined to just one thread. That is, it can change its thread in future. So such a dispatcher which might change the thread of the coroutine in future like this, so it is known as unconfined dispatcher. So again, please note this. Earlier we explored what is a confined dispatcher, and now we saw what is unconfined dispatcher, where our coroutine is not confined to just one thread. It can change its thread in future. Great, isn't it? Now in the end, let us see one more way to create the coroutine context. So here I will just copy the code from here and paste it over here, and then update the code. Let's make it C4 and here as well C4. So in this case, as a parameter, we can just pass the coroutine context property. Now this coroutine context is basically the property of this runBlocking coroutine, right? So this property actually is a part of this runBlocking coroutine. That is the immediate parent if you pass it as a parameter over here. So what this actually means? Well, when you pass the coroutine context as a parameter to the child coroutine of launch, then it will basically pass the context of parent to the child. That is, the context of this runBlocking will be inherited by this launch coroutine. So since the runBlocking was getting executed in the main thread, so that's why it will get executed in the main thread. And also note that it is like a confined dispatcher, right? So that's why right after the delay function is executed, the next statement is also executed in the main thread. Fine, so let us run the program and let's see what we get. So here we go, the C4, here it is getting executed in the main thread, and after delay as well, you can notice it is getting executed in the main thread, right? Great, isn't it? Now, let me show you one more way of proving my point. Let us cut the whole part from here and paste it within our third coroutine, that is C3. So in this case, this coroutine context will be the context of this parent, immediate parent launch coroutine, that is, which is this launch coroutine C3, right? So just before this statement, we have this statement which was getting executed in some other thread. So this some other thread, suppose it is thread T1, will be inherited by this launch coroutine, right? So instead of main thread, this statement will get executed in the thread of T1. And since it behaves like a confined coroutine, so that's why this statement will again get executed in the same thread of T1. Let us run the program and let's see what happens. So let's see C3 after delay. It was executed on this thread. Please remember this, right? So C4 was again executed on the same thread, like we have assumed here, right? This is T1, so this is again T1. And in similar way, C4 after delay was again executed on the same thread as this one, which we have assumed here as T1. Fine. So this is how we create coroutine context in several different ways. Fine. Now coming back to our slide, Well, this dispatcher is basically of 4 types. The first one is the default, then we have unconfined, then main, then IO. Well, just now we saw these two dispatchers, right? But this main dispatcher basically works on the UI objects, and this IO dispatcher is used for IO operations. So we are not going to discuss them right now. We will discuss these two dispatchers in a separate Android tutorial, because it is in Android where we will use UI components and do some IO operations. So for now, don't worry much about them. So for the dispatcher, just remember it is the dispatcher which decides on which thread your coroutine will execute. Fine. Now next we have this job object, which we have already explored in our previous videos. So I guess no need to discuss anything about this right now. Next, what about this coroutine names? Well, you can assign a name to your coroutine and even combine two coroutine contexts together. And also by assigning names to your coroutine, you can debug your coroutine, right? So how to debug coroutine and threads, let's explore that in the next video. So until then, this is Sriyank Siddhartha signing off. Thanks for watching and have a nice day.